Hi everybody and welcome to our chemistry class video for this week. This week I'd like to cover some basic properties of atoms and a little bit of an introduction to the periodic table and kind of see how to use it in some simple ways. So first off, I think we should start with just a discussion of how big an atom is. Typically, and this is a really ballpark figure, it can be quite a lot different from this, but typically an atom is 10 to the minus 10 meters across. That's 0.1 nanometers, if you're familiar with the SI units, or from where I'm from, astronomy, it would be 1 angstrom, which is a very specialized unit you probably don't need to know about. And that's from side to side. That's the diameter of the atom. That's all the way from side to side where the electrons live. Now, if you're talking about the nucleus, it's much smaller. It's about 100,000 times smaller. About 10 to the minus 15 meters. Scientists absolutely love these kind of comparisons. If the nucleus was the size of a grain of sand, the rest of the atom could fit an entire 747 inside of it. So let's talk about some units and measurements. So first off, we're talking about charge, electrical charge. And I always get the question, what is charge? It's a really hard question to answer because it's a pretty strange thing to talk about. In essence, it's a fundamental property of matter that measures exactly how much that matter responds to an electric force applied to it. If something has a lot of charge, then it could be either negative or positive. It'll respond a lot to a big electric force, but if it has no charge, kind of like a neutron has no charge, it doesn't respond at all to any amount of electric force. Charge is usually measured in two different ways, at least with two different units. The standard SI unit is the coulomb, C-O-U-L-O-M-B, which is technically related to how much electrical current flows past a particular spot in a certain amount of time. It's really 1 coulomb is defined as 1 ampere of current passing in 1 second, or an amp per second. We abbreviate the coulomb with a capital C. Most of the time, we're going to be working with really tiny amounts of charge. So there's another unit that's super useful, the elementary charge. It's the charge of both an electron when it's negative and a proton when positive. The elementary charge is 1.602 times 10 to the minus 19 coulombs. It's a really tiny amount. And actually, it's the smallest unit of charge you can find in the natural world. So here's a little technical note that I probably don't have to tell you, but I do want it in here just for completion. Actually, protons and neutrons are made up of these subatomic particles called quarks, which have plus 2/3 or minus 1/3 elementary charges depending on what type of quark they are. A proton has 2 up quarks, which both have a plus 2/3 elementary charge for 4/3, but they also have 1 down quark, which has a negative 1/3, so that adds up to plus 1 elementary charge for the proton. A neutron, conversely, is 2 downs, which adds up to negative 2/3 elementary charges, and 1 up, which is a plus 2/3, so that comes out to 0 charge. It seems, as far as we can tell through experiment, that quarks never exist without each other, so you can never really see these fractional charges outside in the wild, just as part of other particles. And I suppose as an extra note, an electron isn't made of anything but itself, it seems, so it just has a charge of negative E, negative elementary charge. In the kilogram and the gram, basic SI units in this class, and I really hope you know about these from your middle school science classes. You should. And if you don't, go ahead and ask. But the amounts of mass we're actually dealing with are unbelievably tiny. Again, just like with charge. For example, the electron has a mass of 9.11 times 10 to the minus 28 grams. Insanely small. So instead of using really tiny amounts, we're going to standardize on what's called the atomic mass unit, or AMU, which is kind of a complicated unit. It's defined historically in a couple of different ways. The modern definition relies on the mass of a carbon-12 atom, which is a particular type of carbon that has 6 neutrons and 6 protons, and I suppose also 6 electrons in it. So the AMU is exactly 1/12 the mass of carbon. Which doesn't mean that, say, a proton and a neutron are exactly 1 AMU each. They're just a tiny bit more, which is really problematic. There's this thing called the mass defect that we don't really want to get into right now. There's actually a useful table here in our textbook, chapter 2.3, Atomic Structure and Symbolism, right here, that summarizes the properties of electrons, protons, and neutrons. It has charges in both coulombs and elementary charges, and the masses of all these particles in AMU and grams. So for the last few things, let's talk about some useful numbers with atoms and elements, and especially let's look at the periodic table with these. The atomic number of an atom is just its number of protons. We use the letter Z, a capital Z, to denote this. If you add the number of neutrons to the atomic number, that's the total number of nucleons, you get the so-called mass number, or a capital A is what we use for that. It isn't exactly the mass of the atom, but it's fairly close. To go a little further into these ideas, let's look at the periodic table. Here is an absolutely lovely website with great information all about the periodic table and a lot of different visualizations of the table itself. Let's talk really quickly about a few of the symbols and how to read the table. The most obvious thing you might see is the elemental symbols themselves, the big bold letters here. For example, H for hydrogen. Each element has a unique elemental symbol that you'll use in chemical formulas and in identifying these elements. Most of them are pretty self-explanatory, H for hydrogen, Li for lithium, Ti for titanium, but there's a couple in here, especially the very old elements that were known much longer ago, that have some odd names. For example, gold is Au, which comes from Latin. Auricum, I believe, is the actual word. And there's a few others around here like mercury, Hg, silver, Ag, lead, Pb, and a couple others that have a little bit strange names. If you use these a lot, you'll get to know them pretty well, and if you don't have to know them. But the symbol is the first thing. This version of the table has not only the symbol, but the name of the element right underneath it, which is really nice when you're trying to find it. You don't have to use this particular website, ptable.com, but boy, I think it's really fascinating. I've spent probably a couple hours just looking through all the information on here. It's pretty wonderful. So then after the name, below that is the average atomic weight. We'll talk about exactly what that means in just a little bit. But suffice to say, it is an average of all the elements, all that particular element in the universe. The last thing on this version of the periodic table is in the top left corner, the atomic number, which is just telling us the number of protons this particular element has. For example, uranium has 92 protons. Okay, there's a heck of a lot more information we can get out of this table, though. Aside from the different groups or types of elements we have, we can look at the state of each element at different temperatures. So I think black here is solid, blue is liquid, red is gas, and the grayed out ones are unknown, probably because they're too radioactive to actually measure in a lab. And as we raise the temperature, there we go, we were at 280, which is pretty close to room temperature. You can see most everything is a solid. There's a few gases up there, the reds, and a couple of liquids, just a few. As we keep raising the temperature, and we're getting pretty hot now, you can see a lot more turn to liquids and then to gases from solids. A note about temperatures really quickly is you should always say, for example here, 2,891 Kelvin, not degrees Kelvin. There's no real good reason for this, other than the fact that I do know that physicists will laugh at you, from personal experience, if you say degrees Kelvin. When you get all the way up to, 7,000, 6,000 degrees, or 6,000 Kelvin, 10,000 degrees Fahrenheit, pretty much everything is a gas, except for the unknown elements, which are too radioactive to measure. There's lots of other things going on in this particular version of the periodic table, though. You have the Properties tab, and you can go through all of these different properties with different sliders over here, or different types of things. And if you ever need to look up, say, for example, the conductivity of copper, right there it is. It'll give you 400 watts per millikelvin. And that's the thermal conductivity. You can switch it over to electric if you ever need to. Anyway, there's a whole lot of things you can look through here. My favorites are universal abundance. So this little checkbox here tells you what percent of the universe is made of these particular elements. And remember, in the very first lecture we had, most of the universe is actually not matter like this stuff, hydrogen, helium, and so on. It's actually dark matter or dark energy. This is just the 5 or 6% of the universe that's actually made of regular matter like us. But if you want to know the particular abundances of these in the universe, our solar system, in a meteor on average, the Earth's crust, the ocean, or in a human even, you can look through this way. Okay, and actually the discovery one is kind of nice too. You can go through and figure out which ones were discovered when. So before 1730, what you have are basically elements that were discovered in ancient times, and then you start discovering a lot more pretty quickly and filling them up. And there's just a few that were filled in the last couple years. In fact, these last few here have some pretty strange names. Flerovium sounds like something you'd invent in a sci-fi novel. Orbitals, we're not going to talk too much about these. They are extremely cool and very useful if you want to do lots of quantum mechanics. We're not going to, but they look nice. There's some pretty crazy geometries. Like, look at that one. Einsteinium has some interesting electron orbitals going on. We'll talk about what SPDF means later, much later in this course. For today, isotopes are pretty important. This particular tab tells you all the different stable isotopes, and even the unstable ones, of any particular element. So if we look at hydrogen and click on it, it gives us just the 3 stable isotopes of hydrogen. Here's hydrogen itself. I think it's called protium, with just 1 proton and nothing else. It tells us that the abundance of this element, of this isotope, is 99.9885% of all the hydrogen in the universe. So it's just 1 proton. Then there's deuterium, which is 2 nucleons, 1 proton and 1 neutron, has an abundance of 0.0115% in the universe. So 0.0115% of all the hydrogen in the universe is deuterium, but it's stable. And then there's tritium, with 2 neutrons and 1 proton. It says the abundance is 0% here. It's so small, you can't even really write it. And it decays in 12.32 years, is what its half-life means. If you want to see all the types of hydrogen, not just the stable ones, then there's all these. And you can see the half-life of 3 neutrons and 1 proton is 1.39 times 10 to the negative 10 picoseconds. I don't even know what the SI prefix for that is. It's insanely small amount of time, and similar amounts for these guys. And this one with 6 neutrons and 1 proton is even less. And if you go through the table, you can see even more of these. These are all the types of decay that they can undergo. Not super important for you to know right now, but very interesting to look at. The final tab is compounds. Again, I'm not sure how useful this one is going to be for us unless we're really looking into some advanced stuff. But it tells you all the known compounds that each element is involved in. Hydrogen has, for example, 40,796 compounds it's involved in. If you click, you get this enormous list. All these things. And they get pretty complicated, like polyethylene monoalcohol, CH3, CH2, CH2, and CH2OH. My goodness. Others, like beryllium, only have 19 compounds. And you'll notice there's a few on this side of the table that have pretty much no compounds at all. 2 for helium, 2 for neon. It's not very reactive. It doesn't form very much. So all of this idea leads us to the concepts of ions and isotopes. So elements are basically defined by how many protons they have in their nucleus. But at the same time, they can have wildly varying numbers of electrons and neutrons. Most normal matter has the same number of electrons as it has protons, and thus has no net charge. But sometimes it can gain or lose electrons. If it does, it's called an ion. If it has more electrons than protons, it'll be negatively charged, and that's called an anion, A-N-I-O-N. If it has less electrons than protons, it's positively charged, and it's called a cation, C-A-T-I-O-N. The number of neutrons varies a lot. Different numbers for different elements are stable. For example, hydrogen is the most stable with absolutely no neutrons at all. With 1, it's called deuterium, and it's still fairly stable, and with 2, it's called tritium. Anything more than 2 is really unstable and decays into one of the others very quickly, like in fractions of a second. Even tritium with 2 neutrons and 1 proton is pretty unstable. It has a half-life, meaning half of it decays in about 12 and a half years. These variants on elements with different neutron numbers are called isotopes. And our textbook has a table of a few known isotopes. I think it's in chapter 2.3. This is a chart of all the stable isotopes of different elements that we know exist. The central black line here that kind of is straight, but not quite, shows the elements that are actually long-term stable. So the life of the universe, or even longer in some cases. Technically, we have some theories that tell us that protons themselves are unstable and eventually decay into pure energy, which would mean that eventually all matter is unstable. Although we've never been able to prove it in a lab, because the time that it would take for even one proton to decay is much, much longer than the age of the universe. So the further away you get from this central black line, you'll notice that the colors go from blue to green to yellow and even to pink in some places. That follows this little scale on the bottom, which tells you exactly how long those elements live. The half-life tells you really how long it takes for half of that particular substance to decay. If you remember Mr. Grange from last year who taught chemistry, I think he said this was his second or third favorite scientific chart in the world. His first favorite is the HR diagram, which has to do with stars. And if you're lucky, I'll tell you all about that some other day. So the very last thing, let's really quickly do a sample problem like we might have on our homework. We'll do more in class this week. So the atomic mass often listed in the periodic table is actually an average of all the existing isotopes of that particular element, weighted by their abundance in the universe. It's a bit of an interesting statement, so let's try to unpack it with an example. Let's say I have element X, and I don't think there is actually an element with the symbol X as far as I know. I could be wrong, it's not that big a table, so we could look it up. And let's say it has 2 isotopes. Let's say it has one isotope that has 10 AMU and a different one that has 11 AMU. And let's say that most of this element has 10 AMU. Let's say 99% of it in the entire universe is 10 AMU. But there's a little bit, 1%, at 11 AMU in the universe. And this is sort of the proportion. The way we take this, called weighted average, is by multiplying these masses times the percentage in decimal form to get a new weighted mass. Okay, so here we go. Instead of 99, I'm going to be writing 0.99, right, because it's 99%, times the 10 AMU. And I'll add 0.01, that's our 1%, times the 11 AMU. If you go through doing this calculation, I've already done it ahead of time, it works out really nicely to 10.01 AMU on average for this element throughout the entire universe. You could do this, I'll just make up some numbers on the fly. Let's say we have element Y, and let's say it has 3 isotopes. Let's get a little crazy. This is probably not a realistic scenario, but we can still work with the numbers. Let's say element Y, the first isotope of it has, I don't know, 86 AMU is its mass. The second isotope of it has 87. Why not? And the third, let's get a little crazy. Let's say 94. Just because. This is probably not a realistic thing, and I'm sure there is no element that has this particular arrangement. We also want to decide how much percentages these exist at. So let's say 86 is the normal one. So let's say, I don't know, 63% of the universe, of this element Y in the universe, is 86 AMU. We got to make sure this adds up to 100, so let's do some quick maths. Let me make it easy on myself. Put a 7. Let's say 17% has 87 AMU. That gets us up to 80. And then 20% is this 94 AMU version. Again, it's pretty unlikely to have this actual arrangement, but it's kind of an example problem to see how to calculate these things. So in order to calculate the average AMU for this particular element in the universe, we would do our 0.63, that's this guy, times 86, plus 0.17, that's our 17%, times 87, plus 0.20 times 94. And I have just invented these numbers off the top of my head, so why don't you do it along with me? I'm getting my calculator out right now, and I'm plugging these numbers in. See if you can beat me in terms of getting this answer. Times 87 plus 0.2 times 94. I get an average mass for this element in the entire universe of 87.77 AMU. And that's how you do that. All right, and that's it for today, everybody. If you have questions, if you want to do some more practice problems, do let me know, and I'll see you in class in a day or two. Have a good one.